Yep. Hi everybody. I just want to check if this works. Uh, just a second. We want to see if we're live already. How do I see that? I could say here. Just a second. We want to see if. Yep. So I guess we're live right now. Yeah. So hi everybody. My name is Victor, and I'm trying this stuff where I try to go live for a few minutes to do some minor hacking along the side. I'm trying to build in this habit of streaming and showing my work like live. So I think I will start with algorithms because algorithms are something I want to really learn and understand as a software engineer. So I would actually be live streaming myself trying to solve some algorithms. My goal for this is to strengthen my algorithms and also help people understand what it feels like to solve algorithms in real time and put all my experiences solving algorithms for job interviews into like this YouTube channel, so anyone can just binge watch and learn a thing or two about algorithms. So the way I'm going to do this is I'll be trying this for a month, and the way I'm going to do this is I'm going to split the month into like 4 topics. I'm thinking arrays, strings and arrays, hash maps, um, trees and stack, and stack and queues, and then trees. At least these 4 topics for this month, October. So the way I'll be doing this is I will go here, pick a few topics. Let's say wait a minute. Yep, arrays, strings. Yep, array strings and wait a minute, arrays and strings, and then set the difficulty to medium because I want to actually start from medium and then pick a random one. The idea here is to like pick a random question and see difficulty is medium. Yep. And what else? Yeah. And I want to put in the status of what I haven't really solved. So like I get very new challenges. So yeah. So I'll just pick, and then I want to put a timer for myself while I do this. I don't know how to put the timer on the screen, but okay, I know what I'm gonna do. Okay, so let's pick one randomly. So the way I plan to approach this is to give myself a question, set 10 minutes for trying to understand the question and coming up with an approach, 10 or 15 minutes, I'd say 15 minutes for trying to come up with an approach. And if I come up with an approach that is possible to solve the problem, then I give myself an extra 5 or 10 minutes to code the solution. But if in 15 minutes I can't come up with anything, I'm just going to like give up and take a look at the solution and try to solve it with the solution. So let's see if I can add a timer here. Just a second. What the hell? This is working. Yep. I can show a timer here. And then I can reset the timer. And I want it to run for 15 minutes. Ideally. Okay, so let's start. This is the question is find permutation, medium, and is in strings, I guess. So a permutation perm of n integers of all the integers in the range in can be represented as string where n minus 1 length n minus 1. What the hell? Okay, a permutation perm of n integers. So first, permutation of n integers. By permutation, we mean like a combination of these integers in the range I and n. Now, in the range I and n, like I to n, okay, can be represented as a string s of length n minus 1. Okay, where si is I if palm I less than palm I plus 1, and si is d if palm I greater than perm plus 1. Given a string s, construct the lexicographical least smallest permutation perm and return it. Lexicographical, I think what lexicographically means is, let me see this, sorted in a way that uses an algorithm based on the alphabetical order using dictionaries. Okay, given a string s, reconstruct the lexicographical least smallest permutation and return it. So let's see the examples, because it's a bit confusing, to be honest. And so if we're giving input string I, we should give the output I and 2, 1 and 2. 1 and 2 is the only legal permutation that can be represented by s, where the number 1 and 2 construct an increasing relationship. Okay, so the second example is, just a second. Just want to quickly. Okay. Just want to quickly see if I can connect this shit. Yeah. Okay, no, let's just leave that. So let's, given the second example, di, the output is 213. Both 213 and 312 can be represented as di, but since we want to find the smallest lexicographical permutation, we should return 213. Oh, wow. Okay, so let's go through the question one more time. A permutation perm of n integers in all of all the integers in the range I and n. Okay. So what is the, it can be represented as strings of length, where string I equals I if palm 1 less than palm I plus 1. Okay, string I will be I if palm I is less than palm I plus 1. So just trying to understand this. So given a string as, reconstruct the lexicographically smallest permutation and return it. So I don't even understand. Are there hints? Nope, no hints. Okay, so a permutation perm of n integers of all integers in the range I and n. A permutation perm of n integers. A permutation perm of n integers of all the integers in the range can be represented by a string. of length n minus 1. Okay, so what this means is the string we get is always going to be one character lesser than the array that is the answer. Okay, so where si, which is any of the integers in the array, is I. Wait a minute. So we'll be given a string, right? And we have to reconstruct the lexicographically smallest permutation and return it. So for instance, the only legal permutation that can represent S, where the number 1 and 2 construct an increasing relationship. So what is I? Okay, so let's say this one, di 213 2 okay, so let's look at the meaning of lexicographically again. Sorted in a way that uses an algorithm based on the alphabetical order used in dictionaries. Right. Okay, just a second. What is the exact meaning of lexicographical order? Okay, lexicographical order is alphabetical order. The other type is numeric order, and considering following 1 to those are lexicographical order. 10 comes after 2 in numeric order, but 10 comes for 2 in alphabetic order. Oh. So 10 and 2. There. Okay. Okay. I think I know what this is saying. I shouldn't have closed that. So, okay. So, get a string, reconstruct the lexicographically smallest permutation. By lexicographically, we mean a permutation PEM. I'm not even going anywhere with this, to be honest. A permutation PEM of n integers. A permutation PEM of n integers, of all the integers in a permutation PEM of n integers let's see something. A permutation PEM of n integers, that's we're looking for a permutation of n integers of all the integers in the range 1 and n. So we are looking for a permutation of 3. For instance, can be represented as string s of length n minus 1. How do we, okay, this is my question. So if we are given an integer, if we are given an integer I, we are to know that automatically the length of n is 1, 2. A permutation PEM of n integers of all the integers in the range I, 1 and n can be represented as string, okay, of length n minus 1, where si is equals to 1 if permutation I less than permutation I plus 1, and okay, so basically we are going to have a strings of either I or D or I, right? And we asked to find the lexicographically smallest permutation and return it. That's the permutation that is going to the permutation of these numbers that is going to, okay, let's take for example I and D. We know that is going to be 3, right? Like 1 2 3, because S is we can find N by S by adding 1, right? Which is the length of this is 2, add 1 to 3. So now when we say given a string S, construct the lexicographically smallest permutation and return it. When we mean smallest permutation, we mean that, okay, how is 2 1 3 different from 3 1 2? You know, I don't even get this anymore. And I have like 4 minutes left. Okay, so I think something I'm trying to understand right now is we get N from the length of S. Length of S in the second example is 2. So N S, okay, if S is N minus 1, N is S plus 1, right? That makes sense. So given S, we have to find the permutation, lexicographically smallest permutation. Like when you say smallest permutation, 2 1 3 and 3 1 2 like are the same, aren't they? Like they sum up to the same. So I assume we're not talking about. I assume we're not talking about that here now. So what else do we mean by smallest permutation? Let's see. What else do we mean by smallest permutation? Not sure. What else do we mean by smallest permutation? A permutation perm of n integers, of all the integers in the range, okay, can be represented as S, can be represented as S of length n minus 1, where Si is equal to I okay, normally I know that we have to put this in while loop and go through all of them and say something like the you know what? I don't even know. Okay, wait a minute. If okay, we are taking two siblings of this number, and actually, okay, for instance, if this is greater than 1, if 2 is greater than 1, that means is it D, and if 1 is greater than is an I, 1 is less than, okay, I see. So basically what we want to do is, given this string, my time is up now. Given this string, we want to create if it's I, okay, I see. So basically, if we're given a string, we want to we want to first create an array. Oh, no. If we're given a string, what the hell? I can't really solve it though. So let's look at wait a minute. The editorial. First of all, let me get a break. So let's look at the solution. Solution involves a stack, reversing the subarray, and using 2 pointers. Okay, so let's go here. First things first, we are using this stack. Let's revisit the important points of the given problem statement. For example, for a given n, we need to use all the integers in the range I, 1 and n to generate a lexicographically smallest permutation of this n numbers which satisfy the given pattern in a string. Firstly, we denote the lexicographically smallest permutation that can be generated using the n integers from 1 to 3n, say min. Thus, while generating the required permutation, we can surely say that the permutation generated should be as close as possible to min. Now, we can also note that the number generated will be the smallest possible, only if the digits lying towards the most significant position are as small as possible while satisfying the given pattern. Now, to understand these observations help in providing the solution of the given problem. We'll look at the simple example. Say the given pattern D, D, I, D. This corresponds to n equals 8. That's true because 1, 2, 3, 4, 5, 6, 7 plus 1, 8. Yep. Thus, the mean permutation will be 1, 2, 3, 4, 5, 6, 7, 8. Now, to satisfy the 2DD patterns, we can observe that the best course of action to generate the smallest arrangement will be to rearrange 1, 2, 3, because these are the smallest number that can be placed because these are the small numbers that can be placed at the 3 most significant positions to generate the smallest arrangement, satisfying the given pattern till now, leading to the formation of 3 to 1. Because when I is greater than I plus 1, we use D, right? We can note that placing any number larger than 3 at any of this position will lead to generation of lexicographically larger arrangements as cost. We can also note that irrespective of how we arrange the first 1, 2, 3, the relationship of the last number amongst them with the next number satisfy the criteria required for satisfying the first I and S. Okay. Now, when we find the last D in the pattern, we again need to make the arrangement in the last two position only, and we need to use the number 7, 8. Okay. Based on the above example, we can summarize that to generate the required arrangement, we can start off with the number min that can be formed given n. Then to satisfy the given pattern, we need to reverse only those substitutions of the main array which have a D in the pattern. Okay. We need not necessarily create the main array first because it simply consists of yep. To perform the operations above, we can make use of a stack. We can consider the number I from n. For every current number, whenever we find D in the pattern, we just push that number to the stack. This is done so that later on, when we find the next I, we can pop off these numbers from the stack, leading to a formation of a reversed sub pattern of those numbers corresponding to the D's. When we encounter any patterns, it's because we push the current number as well onto the stack, and then pop off all the numbers on the stack and append these numbers to blah blah blah. Okay. I think I'm beginning to understand this. So we have a stack and we have I. We push in 1, push in 2, D. Wait a minute. So this is the stack, and this is the result. So when we encounter I, we push in 1, we push in this, and wait a minute. Let's go back. See how it happens here. Good. So this is what it looks like. So okay. So first, wait a minute. No, don't rush. Okay. So first, when we encounter I, we push 1 to the stack and we pop it. 2, we push 2 to the stack and we pop it. 3, when we encounter D, we push 3 to the stack. We push 4 and 5 to the stack. When we encounter I, we what do? We pop out of the stack, and then we pop all the items into the stack. I6, write 6, I7, write 7, D we just add to the stack, and 9, then we pop all. Wow, I shouldn't have known that in the okay. Whew. So okay, so I think I kind of get the idea here. Just a second. So this is where I really want to understand. To perform the operations discussed above, we can make use of a stack. We can start considering numbers I from 1 to n. For every current number, whenever we find a D in the pattern, we just push that number onto the stack. This is done so later when we find an I, we can pop up all these numbers from the stack, leading to the formation of a reverse sub pattern of those numbers corresponding to the. So when we encounter I in the pattern, we push the current number as well onto the stack, and then pop off all the numbers in the stack and append these numbers to the resulting pattern. Now, okay, this is what the code looks like. We create a new integer array of length s.length minus 1, not s.length minus 1, s.length plus 1. Yep. So we create a new stack and start at j, and then iterate through all the items. If character I minus 1 is equals to I, if this character is equals to 1, we push it to the stack, and while stack is empty, we keep popping. Else we keep popping. Okay, why the stack is not empty, we keep adding to the result array, and then when we empty the stack, or else we just keep pushing items. So after that we get to, okay. After then we push the last item, and then while stack is still empty, we keep pushing, and then we return rest. Okay. So um this feels like a great approach actually. So this feels like a great approach. So we start at this feels like a great approach to be honest. So not sure. Hmm. Okay, so from what I understand, we first we first create an array as the length plus one, and then we first create an array as the length plus one, and then we create a stack also. We iterate all through the numbers. We iterate through s, and for every iteration, we are checking if this number is an I or a D. If it's an I, we push it to the stack. We push I to the stack, and then we retrieve all the items from the stack. And then once we encounter a D, we just keep pushing. If D, push I to the stack. If I push I to the stack and pop all stacks and pop the whole stack. Now like the edge cases at the end is what I don't really understand. So stack dot push s dot length plus one. What does this do? Okay, let's take an example here. Di. Let's take this example Di. We start at I equals 1, I less than s dot length. So this is going to run just once. So if string dot character at this index equals I, else we just push. So we're going to just push 1 to the stack. What is s dot length? S dot length is 2, so this is going to run once. And so stack the push s dot length plus 1, and then we are going to push 3. And our stack is not empty. Wait, let's understand this properly. So result is a new integer of array 3 because length is 2, so 3, and the stack is just a random stack. So we start at I equals 1, I less than s dot length. S dot length here is 2. Why 1 less than 2? This will be really going to run 1. So if s dot character at 0, okay. If s dot character at 0 equals I, stack dot push and empty. But this is not the case, it's a D, so we just push to the stack, and then we have res and just push to the stack, and we have a stack that consists of 1. We have a stack that consists of 1. So we have a stack that consists of 1. So we push the second, and then we push s dot length plus 1. We push 3 now, and then we have 1. We have 1 and 3. We have just a second. 1 and 3. Sorry, 1 and 3. We have 1 and 3, and then we have y stack is not empty. The next is what's in the stack right now is just 1, right? Okay, wait a minute. Let's look at the description of the problem. The example di is 2, 1, 3. Okay, so I guess I was missing something. Editorial 2, 1, 3. So if I equals to 1 and I less than s dot length, this is what we're going to run once. I don't really know though. But if I don't really know though, but if how many times is this going to run? I equals 1 is obviously 1, and then I less than s dot length. S dot length in this case is 2. Why 1 less than 2? Okay, less than or equal to. Okay. It's going to run twice actually. The first time is going to just push to the stack because it's a D. So what is it going to push to the stack? It's going to, okay, let's say this is our stack, empty array for the first iteration. Rest is just an empty array for the second iteration. Empty array with 1, 2, 3. 1, 2, 3. And then it's going to run twice. So as the it's going to push in the first iteration, it's going to push I, which in this case is 1. Right? It's going to push 1 to the stack. And then the second time is coming, it's going to meet an I, and then it's going to push I to the stack, which is 2. And then why the stack is not empty, res 1, wait a minute, res, we're going to pop stack, put 2 here, and pull and pull 1 here, and then that's it. At the end, stack to push 3, which is the last item, and then why okay, and then return rest. Okay, I kind of understand this now. Let's use the second example. Say we're given this already 1, 2, 3, 4, 5, 6, 7. So we know our number is 1, 2, 3, 4, 5, 6, 7, 8. This is what we're iterating now, right? So we start at 1 and check if we start at 1 and check if this number is a D or I. If it's a D, we push to the stack. So let's see the stack. If it's a D, we push 1 to the stack. We push 2 to the stack. If it's an I, we push 3 to the stack. And then we pop all these numbers. 3, 3, 2, right? 1. Is it something like that? Great. So the next one is an I. We write 4 to the stack and pop it. Or write 5 to the stack and pop it. Write 6 to the stack and pop it. And another one, write 7 to the stack and then 8. Okay. That's the first approach, which is cool to be honest. And then the second approach is to use, in order to reverse the subsections of the main array as discussed in the last approach, we can also start by initializing the resultant arrangement res with the main array by filling the items 1 and n in ascending order, and then traversing the patterns S. We can keep track of the starting and any indices in the rest corresponding to these in the patterns and the reverse portion, blah, blah, blah. So let's see how this one works. So we first fill the array. So wait a minute. We first fill the array. Start from the first item. Starting from the first item, we do what do we do? Starting from the first item, we check ij. Okay. Okay. So if we encounter an I, we move the 2 pointers. Whenever we encounter a J, whenever we encounter a D, we move only the J pointer. Whenever we encounter a D, move only J. Move I, and then reverse this numbers. Okay. So the second approach is to reverse the subsection of the main array. Okay. We can also start by initializing the result arrangement res with the main array by filling elements 1 and I in ascending order. Then while transversing this pattern, we can keep track of the starting and end indices in corresponding to the D's in the patterns, and reverse the portion of the subarray corresponding to these indices. Okay. Because we're traversing ones, right? This is a very good solution for this this is also a very good solution, O of n, but space complexity is O of n because we're also adding the stack. But in this case, there's no adding of the stack, which makes it a good solution. I like it. So basically, okay. So basically we basically we started out at with the 2 indices, and we keep moving them, and we move I when we encounter like D, and then whenever we encounter an I after D, we kind of swap. Okay. So this is a reversing the subarray. So we reverse the subarray actually. So here you see we first instantiate a result array, and anytime for less than result length, result 1. Okay, so fill up the array with integers. So why I then look through all the strings, J equals I. Why if it's D, if it's a D, okay. Wow. Okay, so the next one is the 2-pointer approach. Instead of initializing the res array once with ascending numbers, we can save one iteration over res if you fill it on the fly. Okay, wow, this is a good solution. I feel like I kind of understand it at least. Man, I feel like I like this solution better, the second one, because I like this second one better, but it's all good. It's all good, and I think I can end this session here. Wow. I think this is a good first problem. It was quite difficult to understand, but I kind of get the idea around it, and I'm just tempted to go back to the medium to easy questions, but I don't know. I feel like it's going to be worth it to do medium ones because I'm going to see harder questions, and yep, I guess that's it. I would ideally want to code it, but I'm just exhausted. The questions are quite difficult, to be honest. So yep, see you tomorrow. I'll do the same thing.